Here we are in chapter 10, the final of the big concepts of the class. That is the concept of area. What we need to do initially here in section 10.1 is define the concept of area. And we also need to state the three postulates for the chapter, the three initial postulates. We'll have one that concerns similarity in area later on. So just a little bit before we do that, though, about how it is that I'll approach this chapter. Typically, the way that area is taught is honestly terrible. What students are given is just simply formulas, and then they're asked to put numbers into the formulas and say the numbers will take it back out with little justification for why it is the formulas work. You're familiar with them, like the triangle area formula or the circle area formula or whatever it is. We will not do that. That's terrible. Instead, what we'll do is this. We'll derive the area formulas and we'll put them together, put them to use, in good problems. And when I say derive, I mean prove them. Typically, the word that's used in this context when we talk about formulas for area is derivation, but a derivation is simply a kind of proof. It's often strongly algebraic in flavor, at least part of it, but it will still be a proof. All right, so first of all, let's talk about what we mean by area. First of all, you have to understand that this is a new way to measure. Previously, we've had two ways to measure geometrical objects. We've measured segments, we've measured angles. Of course, for segments, we have length, and for angles, we have our preferred unit is degree, so we have degree measure. Now, notice that in both of these cases, that is for length and measure of an angle, we have to establish a unit. Now, as for length, we didn't worry too much about that at all. It can be whatever you like, centimeter, inch, mile, kilometer, whatever. And then when we give the length of a segment, we've said how many of that unit is present in the segment. And it's the same for angles as well. The unit that we prefer is the degree. And we then say that the number of degrees that are in an angle is the number of that unit that it takes for one side of the angle to rotate to coincide with the second side. So whatever the kind of measure it is that you use, and this is universally the case in the sciences, one must first establish a unit. So in the case of the square, in the case of area, we must establish a unit as well. And the typical unit here is the unit squared. That is a square of side length 1. And then to say that a particular region has a certain area means to say, what that means is that it takes that number of unit squares to cover it without gap or overlap. So for instance, if you say that the area of a certain region is 12, that means that it takes precisely 12 unit squares to cover it without gap or overlap. Now, that doesn't mean that 12 unit squares will fit perfectly into that object without dissection. You might have to cut them up and put them back together in some fashion, as is obviously the case, say, in a triangle. And then it becomes a good question. It's like, how then do we know how many unit squares it takes if we have to do some sort of dissection procedure? We'll get to that. But no matter, still, the area of a figure is the number of unit squares that it takes to cover it. Now, just before we hop into the postulates, what this means is that even if you did not know an area formula, at least for certain simple kinds of figures like the one that you see in front of you, the rectangle, one could say what the area is. Even if one were to imagine that one had never encountered an area formula, for instance, never had encountered a rectangle area formula, then if you understood the definition of area, you would be able to say immediately that the area of the figure in front of you is 8, because obviously it contains 8 unit squares. Now, postulates, okay? We have our basic definition of area, where we set up our unit of measure and we say what the area of a figure is. We need postulates as well. And these postulates, together with the results of the previous chapters, will combine together to give us the means to prove the area formulas of the chapter. So, the first area formula. And this should come as, not formula, but postulate. This should come as absolutely no surprise. As I have said, we now have 3 ways to measure geometrical objects. We have length for segments, we have degree measure for angles, and now we have area for regions of the plane. And for each of these, we have an addition postulate. We had the segment addition postulate, we had the angle addition postulate, and now, of course, we have the area addition postulate, which says, roughly, that if you take a region and you divide it up into subregions, without gap or overlap. Of course, gaps would mean that you don't have it all. Overlap would mean that you have too much. So if you divide it up into subregions without gap or overlap, then the sum of the area of the subregions is the area of the region, which is just a particular instance of that general principle. If you take some whole, whatever it is, and cut it up into parts, the whole is the sum of the parts. So this should seem obviously true. Second is the area congruence postulate, which says this, that if we have two congruent figures, they must have equal areas. So for instance, if the pentagons that you see in front of you are congruent, and let us say that they are, then it will follow that their areas are equal. This seems to me just blatantly obvious as any postulate that we have encountered. And then finally, our third postulate does count as an area formula, and it's the area formula for a square. And what it says is this: the area of a square of side length s is s squared. Now, of course, the area of a square of side length 1 is by definition 1, because it takes 1 unit square to cover 1 unit square, obviously. So now in this case, we extend that, and we have a square of side length s, and we will say that its area is given by the expression s times s, that is s squared. Now, I will, of course, not attempt to offer you a proof of this. I called it a postulate, so that signaled that I mean for you to assume that it is true, and I will offer you no proof of it. However, that doesn't mean that one couldn't look at examples and motivate it and to understand better what it says. So here's an example. So let's say we have a 3 by 3 square, the one that you see in front of you. Obviously, that just is a 3 by 3 grid of unit squares, right? So it's 9 total. So what did we do to the 3 to get to the area? We multiplied it by itself. So that sort of example, I think, should motivate, should make the square area postulate seem obvious. So one final little matter. This will be discussed in greater length at the end of the chapter when we bring in similarity and we discuss connections between similarity and area. But let me go ahead and make sure that you don't make this mistake. You are better than this mistake. You are not worthy, or you are more worthy, I should say, than a mistake like this. But students will do it sometimes, and they'll do it just like without reflection, and just think that it must be true, but it isn't. Here's what I mean. So let's say that we have a figure, a polygon, let's say, and let's say we scale it, okay? We scale it by a factor of 2, which means, of course, that all the side lengths get multiplied by 2. And then we consider the area of the figure that results. Students will sometimes say, well, of course, the area must be twice as great as it was before. And I say that no, that is the mistake that you are better than. You should not do this. And once one looks at a simple picture, I think one realizes why this is obviously false. So let us say that we have a square. Okay? So it's a 2 by 2 square initially on the left-hand side. And then let us double each of the sides. So this becomes a 4 by 4 square. So initially we had an area of 4. Is the area of the figure that results double that? Obviously not. The area of the figure that results is double the double of that. That is, it is 4 times as great. And it should be clear why it is that this happens, right? Because when you scale a figure like a square, you have scaled in each of 2 directions, right? In the case of the square that I've shown you here, one scaled vertically and one also scaled horizontally, right? Now, if one had only scaled, let me draw a little bit for you. If one had only scaled vertically, then one would end up with a 2 by 4 square, and yeah, the area would have doubled. And if one had squared only horizontally, then the area would have doubled. But one did both, right? One actually scaled both horizontally and vertically. That is, each of those 2 dimensions doubled, which means that the area must be 4 times as great. And in general, the result is this, and I will elevate this to a postulate later on. The general result is this, is that if you have a polygon and you scale it by a factor k, the area after the scale is k squared times what it was before. And again, the reason I bring this up is not that we'll use this so early in the chapter. It only comes up later, but it's a common mistake that students make, and I just wanted to go ahead and nip it in the bud.